Yeah, is the screen visible?
Yes, sir.
Okay, good. Okay, just to have a brief summary, what we did was we stacked layer upon layer single perceptrons. So each perceptron, as we can see, is a linear classifier. So one blue line is basically can be done by one perceptron. So if the data is not linearly separable, therefore we go into stacking of layer by layer, which we call as neural network, where actually what we do, we cut this whole space into fragments, and in between it we can denote that something is a class A or a class B beyond that particular region. So it's a logical combination of perceptrons which resulted us in the neural network. So in the right side, you can see that the neural network, the only change we made is that instead of the threshold, which is hard, we made it at a logistic function, which is a soft threshold. There are two interpretations of it. One is the probabilistic interpretations, that sometimes we want something to be of 0 and something to be of 1. But in between it, there is a little bit volatility we want to keep it, which is a linear somewhere, but it's not fully 1 or fully 0. However, we need to make a decision boundary. So whenever we go beyond 0.5, that is our sum goes beyond 0, we make it as +1. And whenever the sum goes below that, we make it as other class. And we have seen that there are hidden layers inside it, and there are input layer and there are output layer, where each layer is basically consists of a set of nodes which are a summation followed by a logit or a logistic unit. And if we try to write the equation for this, the final, so we first assume that there are L layers, and the small l is from 1 to n, and the input layer we call it the 0th layer, and the final layer has only one output block, which is only one particular such kind of a logistic unit. So therefore, every unit, the jth, the at the layer L, the jth unit output is given by xj subscript superscript L, which is passing through a theta, the sum that it gathers from all the inputs that come into jth layer. That is L minus 1th layer, ith block input in L minus 1th layer, all of them. So there are dl minus 1 number of them. I sum it over and pass it to the logistic function of that particular node in layer L. So every layer has this functionality. And this theta is a smooth logistic curve, which sometimes called as a logit or a logistic unit, where we can take 1 by 1 plus e to the power minus s. This is a conventional theta s. Tan hyperbolic s is sometimes taken, but mostly we take this one, where it has a beautiful feature that we can make a derivative out of it, and which can be expressed by theta s itself, as we have seen in the last class. Now the question is that, suppose we are following stochastic gradient descent method in order to make sure our weights form a very good boundaries in the final classification. So what we do, we take each of the training example, we pass it through every layer, come up with an output. Depending on the error that we made in the output, we try to propagate back and update the weights of the layer. Again, take next example, push it through in the forward direction, compute the error, again make it back, tune my weights, and go on doing this until we reach a minimum. So therefore, the fundamental thing that we want to do, we want to make the change in the error with respect to change in every weight ij at layer L. This we want to compute every time, because if we can compute this, this is actually, I mean, this will lead you to the fact that this is basically the update of the weight is minus step size into this, as we have seen. So every ij lth update is the previous weight plus delta wij. Delta wij is nothing but minus eta into this. So as we have seen, the chain rule gives us the fact that I can write it using del EW by del Sj into del Sj by del Wij. There is one interesting observation here. So this particularly I call it del J of layer L. And the beautiful thing is that since it's a network which we are going from backwards to the input side, so we can recursively compute the change of weight error with respect to weight and divided by del Sj, which is the sum at the jth node at layer L. However, this one, the del Sj by del Wij is nothing but xil minus 1 input, because if you see this is the sum, so this is the sum, and what you are doing is that you are only deriving it with respect to Wij at lth layer. Therefore, only xi at L minus 1th layer will be present, rest of the term will be 0. So this term gives me this. So now we want to, the only thing in this expression to compute is del JL. So we will compute it recursively since we are going from backwards towards the beginning. So our recursive base case is if I can compute the last layer, and then I will assume that at any intermediate layer I know this, what will be that for just previous layer. That's how the recursive process goes. So at the last layer there is only one unit, so the J is 1. So del 1 at the layer capital L will be this one, as you know, and as our error is a square, half I take it after derivative to cancel, so a squared error between the actual output and the observed output. So if you take a derivative where theta is equal to x1l in that only one layer at the output, you will get this one as we have derived. Just derive it and place theta s equal to x1l, you will get this one, nothing else, because theta dot s is this term, theta s into 1 minus theta s. So this is one step computable. Since our base case is done, now I need to compute what is the value at the ith node of layer L minus 1 del value. So that is basically I will try to form a recursive formulation. So this means this one as per our definition of del, which is basically this particular del at ith node L minus 1 layer. So when I am coming back, so let's say this layer can get feeding, coming the backward feeding from all of these layers, because all of them are connected to this layer. So when I'm coming back, just observe the blue lines here. So this theta also comes back here. This theta, from theta I can come back here. So every theta nodes are here, I can come back to this. So all of them I have to sum up for the lth layer. And then similarly, I can go a chain of expressions that del We by Sjl, del Ew by Sjl, del into del Sjl by del Xil minus 1 into del Xil minus 1 by del Sgl minus 1, because I finally need this one. So this one is, again, I know that next, the immediately following layers del JL, which is recursively computed, and I am computing that calling the function here, because I am computing backwards. Initial case is the last layer, then last to last, then third last, then fourth last. In this way, I can come back and compute L minus 1th layer del from this. This value is again Sj is deriving, I am taking a derivative, partial derivative of Sj with respect to xi, which is, if you follow the sum equation, only Wijl will remain, because others will term will be 0. This one is a popular term because this one is nothing but xi is the output of theta, Sj is the input of theta, that is I am just deriving my theta. So if you just write it this hairy equations into a little bit structural form, theta dash xil is xil minus 1 into 1 minus xil minus 1, because I know theta dash s equal to theta s into 1 minus theta s. This term, summation term, I put it as it is. So the blue box is here, the red box, the recursive call is here, the green box is here. So what we finally get is that I need to update the weight, as I said, is minus eta is my learning rate or step size into this. So I minus eta into del ijl into xil minus 1 that I have written here, where each level del ijl is I can compute by back propagation algorithm. So this is where we ended in the last class. Okay.
Yes, sir.
Okay. So now the thing is that 2-3 things to note here. We call it as a feed forward network because everything is moving forward in deep learning. So the whole work of deep learning starts with the premise of this neural network and backpropagation algorithm. So their networks are deep because There are many hidden layers. And sometimes we not only have a forward link, we can have a backward link also. So those networks are of different convention, and sometimes we call it that we take certain functions and then compose it and take the value to the next layer. We call it as a convolutional neural network. We convolute and push it. Sometimes what we do is that we give a timestamp that the ith timestamp value of this goes to the I plus 1th timestamp value of the next layer. So that we call it as a recurrent neural network. So there are many variations, and which is obviously the course deep learning goes through all these variations. And the other thing with respect to the bias of this particular network and the variance, we will gradually move in when we move into the theoretical side of it, the generalization, regularization, validation, bias, and all that. But typically people try to validate it in such a way that they take the examples, they go for stochastic gradient descent, and sometimes do cross validation, or sometimes stop if they reach a local minima by saying that del wij doesn't change much with respect to a set of examples they proceed. And we call this one forward pass and updation of a weight is called a epoch. EPOCH, epoch. We call it one epoch. It may be all examples together. It may be k set of examples one side. It may be one example. So the training, the epoch is the forward path of training. One forward path fully is one epoch. So this is what we finally concluded in the last class. So if we recapitulate, see, now we are at a position in the machine learning class now that we know multiple methods to do classification and some methods to do regression as well. So if you can see, we have three types of problems we tackled. One is classification problem, which we tackled using linear models, perceptrons, neural networks, classifications maybe with multiple things. We targeted the real valued regression problem, and we also have a probabilistic interpretation like Bayes classifier, Bayes network, and here also using a logistic unit, that impression is probabilistic, and we can see that movie rating, heart attack prediction, stock markets, predicting whether to give a loan or not, how much value of loan to give, such kind of problems we can, from the data, we can do a supervised learning as we proceed. On the next course, we will just little bit move towards that. We have seen the weapons to solve problems using machine learning. Now we need to evaluate such weapons. So how good we are doing in terms of classification algorithm that we are giving. What is the bias? What is the variance? What is the limit? Only in the initial class, I told you about the feasibility of learning, that possibly we could be bad, but probably we are not so bad. So how can we generalize? All these concepts will come in. How can we evaluate a classifier? So from today's lecture, with a set of lectures over the next few weeks, we will try to dig down a little bit of the theory, but mostly with the intuitive notion of how it is doing, good or bad, or how can we improve it? What does it mean? To start with, I will just start with a very simple efficiency calculation. So essentially what we are given with, a feature space. We call it a feature space where there are certain attributes. So the attributes are x1, x2, and with respect to that, I am given certain points to classify between them, these set of points. So effectively, we are trying to solve again the supervised learning problem with an attribute set to the set of y, where I can say y is +1 or -1. It's a two-class classification problem. Now, usually we try to analyze a discriminant of this. So discriminant means which can classify both of the classes. And as we have seen, that if we use a certain linear model, we will get something like this. If we use decision tree, we might get something like this and this. If we use neural networks, so we might be getting like this, this to classify the plus. So all of them are different models and different discriminators. So the problem we tackled in terms of classification is also known as discriminant analysis. We want to analyze a discriminant, and this is in terms of the linear boundary y. So you may also figure out certain discriminants which is transforming this space into a nonlinear zone, and then moving it back may give you such kind of a discriminant as well, right? As we have seen such examples. So if we now as you know that we start with very basic models. So instead of this only discriminant anything, let us focus on the linear discriminants. That is, only with a linear line, how can we proceed? So if I draw the linear discriminant again in that feature space, so this is my x2, this is my x1, these are the positive points, these are the negative points. Now you can see that linear discriminator, I can draw many. I can draw this way, I can draw this way. Okay, I can draw this way. There could be many linear discriminator. So, however, among all such discriminator that you can draw, how do you know which one will classify it best? So let us make it a little bit more formal. So any linear discriminator we draw ultimately is of the form, in case of 2D, it is of the form, as you know. So this is the line, that equation of the line, right? And for any new point that we want to classify here, so suppose I given a new point, which is, let's say, A1 and A2, you want to classify it here. So what you want to do is that in this new point, you will just place it. So if W1 A1 plus W2 A2 plus B greater than 0, let's say greater than equal to 0, you class it as +1, right? If it is less than 0, you class it at -1. That means if it is more, then it is in the right side of the line. If it is less, in this side of the line. So this side is positive with respect to this line, and this side is negative with respect to this line. That's how we classify any new point, right? Now, how do we know that which one is the best? What does the common sense say us? To see that, if I choose this line, is it very good rather than choosing this line? It is not, because you see there are some points, if there is a point like this, then your this line is much better, right? Because it indeed classifies positive, and also if you see the locality of this point, it is more tuned to be positive than negative. However, this line misclassifies it, right? So depending on this insight, just think of common sense. What is the best possible discriminator, linear line discriminator, can you put here? Any of you? Anyone? Yes.
For a line that passes through the middle at an angle of 45 degree.
Absolutely. I mean, angle of 45 degree in this case, you might say, but I mean, it may not be always the angle of 45 degree. It depends on the point, but this is the basic intuition that we will follow, right? I mean, we will try to pass something. Let me draw it in a different color. We will try to pass something which is almost middle in these both classes. That would be my ideal discriminator, linear discriminator, right? In the middle. Now we have to define what do we mean by middle. So for that, if you see the discriminator line that we drawn here is basically of the form of WTX plus B is equal to 0. Or you may also say it as a W1x1 plus W2x2 in 2D plane plus B equal to 0. This is the form. And any point, let's say if I take a point xi, okay, any point xi I take, it is level as positive or negative, any point. So if this value is more than 0, that point will be positive or more than equal to 0. And if this value is less than 0, that point will be negative. That we understood. Now this is the level of that point, yi. So therefore, my first condition, I am just coming theoretically a little bit. My first condition, looking into these constraints, I can say for a line xi, yi into w1 xi1 plus w2 xi2 plus b will be greater than 0. Right? I mean, greater than equal to 0, to be on the more safe side. You get it? Because any point, if it is positive, then your yi will be +1 and this value will be more than 0, more than equal to 0 in these cases. So it will be greater than equal to 0. If it is less than 0, then your y will also be -1. So both of them minus will again make you positive. So this is one of my conditions that should be followed in the discriminator. I am not saying about it is the best or not. Agree? Yes or no?
Yes, sir.
Sir, I have a question.
Yes, tell.
Sir, the yellow dot were put in the graph.
Yes.
With respect to that point, we have decide this thing. But if the point is some another word, then might be the straight line is better. It might be na.
It might be better. That's why we want to find the best one. See, our best one, if you are only given the training point, how do you know the best one? Best one would be somewhere in the middle, right? Now, middle is a word. I need to define it. I will gradually define it. See,
Okay,
this is much better than moving it from here or maybe here, right?
According to middle, with respect.
According to the middle, but it's an English term. I will go on theoretically define. It's our intuition that somewhere the class here and the class here, the line should pass in between them in the middle. Okay. So this is condition 1, as you can easily see. Okay.
Okay, sir.
Now see, how do we define middle? Is our next thought. So one of the way that we can take perpendicular distances of every point into this line, right? Of every training point into this line. So what is, let's say for a training point xi, what is the distance, perpendicular distance with this line? The line you know is this. Isn't it? Coordinate geometry. The root square of the slopes, and then we do this as an absolute by putting the values of the point in the line. Right?
Yes, sir. Yes, sir.
Therefore, what I want to do, I want to find, so I want to see, so this line should be put in such a position where the minimum distance is maximized. Do you get this point? What I want to do, I want to find minimum of this distance. That means this point distance or maybe some other this point. Let's say these two distances are the minimum. And I want to maximize that minimum distance to make it inside the middle. Clear?
Yes, sir. Yes, sir. Totally.
So
Everyone?
Please repeat. No, sir. I didn't understand why we'll maximize this minimum distance.
So what is the minimum distance? That means the line that you are saying as a discriminator or separator, the point is nearest to that line, right? What do we mean by minimum distance? A point is nearest to the line. I want to place the line in such a way that among all such points, the line is best placed. That means maximizing the minimum distance between all such points.
Yes, sir. Got it.
Yeah. So therefore, you can see it's a problem where we want to maximize the mean I with respect to W1 x I1. I am only doing for 2 dimension. You can easily extend this one with WTXP for higher dimension. But if you understand this, you can easily do it over higher dimension as well. So as you can see, this minimum is not dependent on the denominator. It's only dependent on the numerator, right? It's only dependent on the numerator. This is another observation. The second observation, the line that we took, it could be anything. Suppose your line could be 2x plus 4y plus, let's say, 12 equal to 0. It could be 4x plus 8y plus 24 equal to 0. It could be x plus 2y plus 6 equal to 0. All of them are linearly dependent in terms of coefficients, so all of them are same line, right?
Yes, sir.
All of them are same line. So which one we will take? Which one we will take as my discriminator in my equation? So
Second one.
why do you think second one? This one, why do you think?
For the term 24, highest from the other two.
No,
6
it
and
could be
12.
more. Na, I can multiply it with say 1000 to everyone. That could be another line. All are linearly dependent, so they all are same lines.
Yes,
Sir,
yes.
Yeah.
so one thing we can do is we can divide all the three lines by root of coefficient of x square plus coefficient of y square. Then all the three lines will reduce to same equation.
True. No, I am saying that any of them represents the same line. That is not a problem. But if you reduce also, it will be the same line. So
Yes, sir.
how do we select my W's and B's in to minimize this one? See, one thing I can do for my theoretical easiness is that when I say minimize this one with respect to point xi, I can choose W1, W2 in such a way that the minimum distance point gets this value to be 1. I can do that, isn't it? I can choose a W1
Yes.
and a W2 in such a way that among all points, which I gives me the minimum, for him, my distance of this numerator computes to 1. I can choose W1, W2B in such a way. Why I did that, then my maximization, this maximizing the minima, this problem only boils down to maximizing something called as this, where this C is nothing but a short form, as we know that this is a double norm, which is WTW, which means it's a vector of multiplying like a column vector with the same row vector, which is this square. So effectively, this one I am trying to do. Agreed till this point? So my question comes to maximize this one finally.
Sir, excuse me, sir. Can you please once again explain the numerator term being 1?
Yeah, I am saying, see, minimum I, that means among all the training points are given to you, you want to take the training point from which your perpendicular distance is minimum. Isn't it? This inside whole
Yes, sir.
term will minimize if you can take a training point from which the perpendicular distance is minimum. For our case, this is the point. Now, I will select the W's and B's of that line in such a way that feeding that point here gives me the value as 1. I can take W's and B's in such a way anyway, right?
Sir, yes,
Keeping
sir.
the line intact. So that what it helps me to simplify my optimization problem.
So, sir, why 1? Why not 0.5, 0.2?
0.5, 0.2 looks good or 1 looks good? Which
One
simplifies
looks
it
good.
more. You can take any constant, by the way. You can
Oh,
take
okay.
any constant. It looks good. I mean, you can take any constant.
Okay.
So therefore, your thing comes that this with the constraint being this while you choose a line. Now wait a minute. When I say that my minimum distance to a point, this one is minimum 1, then I can update this equation, right? This would also be 1 because the minimum of any point is more than equal to 1, isn't it?
Correct, sir.
Yeah. So when you understood the clutter, we call it as a primal optimization problem that we are going to solve. Is that we want to minimize 1 by root over this norm, which is effectively telling us that you maximize right. I can tell that because this is root over W transpose into W. I mean, if I flip it, then I will have to maximize this one. And I took a half because to take a derivative, it will be easier. I mean, the square terms will go. That's why I took a half. Agreed? Subject to the constraints which I have in my hand is yi into this is my optimization problem that I would like to solve for getting the values of W's and B's. Clear? So all being said and done, what we are trying to do, if I just to get a good view for the whole thing, is we are trying to pass a line which is basically basically in the middle somewhere, so that the perpendicular distance between all these points is the minimum, and I need to maximize that distance so that fit it exactly in the middle. Right now, you can sense one particular thing. See, in both sides there will be 2 points which will support this line to stand inside the middle with this condition optimization being solved.
Yes, sir.
Yes or no?
Yes, sir.
Because if you push it in this side, then this point will get annoyed, and if you push it in this side, then this point will get annoyed. So somewhere in the middle means there will be at least 1 point from both classes which will support your line that you intuitionally get as a middle. So we are leading to the concept which is called as a support vector machine model. This is the intuition behind it, that if we can solve this one, we are in a business. However, solving this one in the present form, where we want to maximize this subject to the constraint, this one is a little bit non-trivial. Rather, people transformed it into a dual optimization problem, which we say. So we are not going to go into the transformation details of it, but both are equivalent. So this is in the any optimization book. If you open, you will get this transformation. So what they do, there is something called a Lagrange multiplier. So for each point xi in your training set, they have something called alpha I, which is called a Lagrange multiplier. This is just a mathematical, I would say, transformation. So just try to follow this because the proof is a little bit big, but it's there in any optimizations book. So there, what they do for each xi, they try to. So the intuition of the proof is that instead of a constant being such a clumsy term, they want to make the constant that each alpha I will be greater than 0, that much. So they want to put the constant this way, but however they want to. What I would say, what they want to do is the optimization term, they will try to make it big, and there are certain advantages. I will mention those advantages. What they do is they try to maximize. So instead, if I call it L, they try to maximize the L, which is not only this anymore after the transformation, but also with respect to all the points that you have. Suppose you have n number of points. This So this is this minus 1 into alpha I, they multiply the Lagrange multiplier and they try to maximize this value with respect to these constants. why they did it, because if we try to do maximization as per our regular rule, so what I want to make this equal to 0 and I want to make this equal to 0. So to make this equal to 0, if you do this equal to 0, you will get W minus, so del L by del W this equal to 0. So from this term it will be W is coming, because it is some W means some Wi, so only that Wi square will participate, the rest terms after derivative will be 0. So if you take this one, then here the W will come, minus here if you see this term, as you can see alpha I yi b, this term with derivating with W will give you 0. Similarly alpha I yi with 1, this term will also give you 0. The only this inside term, and taking the derivative of this inside only one term, you will get nothing but it is a yi alpha I into xi. So this is 0, which implies the finally my W is yi alpha I xi. Remember our alpha i's are constant, it should be more than equal to 0. Similarly, if you take the second derivative, this one with respect to b, so with respect to b, this term goes off, everything goes off except alpha I yi remains in the summation. So summation I equal to 1 to n alpha I yi, this will be equal to 0. So finally, if you go there, then so this is our second condition. So we do not have to go anywhere, but this is our second condition. So what we get in this formula is, by derivating and taking the minima, is these two form. Let us try to analyze this one. What does it mean? So you have, so this means that, see, what does Lagrange multiplier is trying to do? You have points, that these are my xi's, the points I have in the space. I am trying to multiply a greater than or equal to 0 quantity and then trying to multiply the level with it. So it means it is trying to enhance the vector in all these directions and then trying to take a resultant vector of them, isn't it? It is just the same. The value xi multiplied with the Lagrange constant with its label, it's trying to take the resultant vector of it. That is your final weight vector. However, if you look at it closely, that in practice, since alpha is greater than equal to 0, not every of the alpha i's are actually more than 0. Many of them are equal to 0. In fact, if you look at the support vector concept, only the support vectors will give you more than 0. The rest are equal to 0. So this is computationally very efficient, number one, to compute the weight. Secondly, you will see that if I compute the W, my B computation is very easy for the line, because I know the line equation is WTX plus B equal to 1. So if I know the W, my B is nothing but 1 minus WT of X. So I can easily compute the B from here. So, and in colloquial terms, we call W, you know, we call it as a weight vector, and B we call it as a bias, because as you know that the B changes, the line shifts from the direction parallel to it. So it's a threshold shifting of the line, so we call it as a bias. Now with getting these two final values, we need to plug it into the L, because we are maximizing the L, and L will be maximized when my W is this, and my with respect to B I got this condition. So finally where I end up with is, my maximized value of L is half WT into W. So if you take this and try to do it, so this will be half WT into W. So let me just put the values. So this is half this into this. So summation I equal to 1 to n, summation I equal to 1 to n, both should be multiplied, right? Alpha I, alpha j, yi, yj, and xi dot xj. This is a dot product between, since xi is a vector of attributes, minus now this term. Okay, so let us do it. This is it. Now this term is 0, so this one cancels. This term is 0. These two terms are the same, so I will just only have a half of it. So finally, I come up with summation of alpha I, where I equal to 1 to n, minus half, because plus half and minus 1 is minus half, sum of I and j, alpha I, alpha j, yi, yj, xi, xj. So that is my minimum, that is my maximized value that I want to maximize for this line to be better placed in the best position. Now see here, this term computation is much easy if we pre-compute this part, because these are all xi yi combinations. That is my n number of training examples. Looking at the training examples by a single pass, I can pre-compute this and then multiply with alpha and alpha j and take the sum every time. So pre-computing this into a matrix, we call it as a Hessian matrix. So let me again come back to the same equation where we find, therefore, our finding is three things. Therefore, we found W to minimize is summation I equal to 1 to n alpha I yi xi, and we found summation I equal to 1 to n. When I minimize del with respect to del b, del L by del b, I got this one. Finally, I got this one, which is summation alpha I equal to 1 to n minus. This is simple algebra. See, I just did two derivations. I put up this value in this particular L. Nothing else. It's a simple algebra. It looks very bad. It's very hairy, but it's a simple algebra that we did. J equal to 1 to n. I have alpha I, alpha j, yi, yj, xi dot xj. Now, what I'm saying is that I will try to keep this thing into a matrix, which is often called as a Hessian matrix. So it has, so this will be a matrix, and in between some term that I will compute yi, yj, xi, xj, and keep each of the terms here. So this matrix is my Hessian matrix. I call it as a Hessian matrix. So to reduce the clutter, this I can write it. So if I take all the alpha I vector as alpha 1, alpha 2 for the n point alpha I vector as 1 cross n vector, and let us take a unit vector as well of n dimension that I will require anyway, which is of also 1 cross n. So with that, I can just reduce this one. You see, I can write it this minus half of, this is my h, as you know. So therefore, I only need to do is half of this. So this is my h transpose, for one for alpha I, one for alpha j, to transpose, because you need to compute a particular one expression. So what does it do is that it is, after this transformation of this, is basically it can be solved using something called as a quadratic programming. It can be solved using quadratic programming because this term, as you can see, is quadratic with respect to alpha. This one, it is quadratic with respect to alpha because my Hessian matrix is a pre-computed matrix and it will give me a value whenever I ask for it. So it is quadratic in terms of alpha due to these relation. So it's a quadratic programming that can solve this. After solving this, what we will get, so after solving this using quadratic programming, we will get the values of alpha i's. So after solving this, we will have in our hand the values of alpha i's from this using quadratic programming. Now what we will do, our job is, finally I know that I need to plug those alpha I values into these equations. I know for every point yi, xi. So these equations to get my weight, and I know that my bias will be computed by 1 minus for each of the x's. My bias will be computed. So let me come back once again. We have this constraint greater than equal to 0 in the beginning cases, because this is the line, positive side is 0, more than or equal to 0, negative side is less than 0. So when I multiply yi, so the negative is -1, this is also negative, make it more than 0. Now this line could be of any equation, but however I will choose a particular weight and bias so that the minimum point through which it gets supported, now we know the word supported is basically comes this value as 1. So the minimization part, I could just reduce it to only a maximization problem rather than a max min type of a problem to make my computation simpler. So when I did it, so it's a maximization problem of the same this thing with a constant of this, which is more than 1, because my minimum support distance is becoming more than 1, more than equal to 1. So the equal to 1 rather. So every other point should be more than or 1 than this point. So this value is greater than equal to 1. This is +1 or -1 gives me this side as 1 instead of 0. Now what I will do is that, so in tomorrow's class I will tell you, this is called KKT theorem. Okay, Karam-Kuntaka theorem. So this is an equivalent dual problem. I will convert it because I have a weapon called quadratic programming technique, through which I can solve it, where the constraint I need to reduce it with a single one instead of this vast constraint. So I need to optimize this one. What I did, I introduced something called a Lagrange multiplier and just multiply the equation -1 into alpha I for all the points. So every point that is not a support is actually making it more, reducing the maximization factor a little bit more. With that value, I try to compute the derivative with respect to w and b. As we know, we do it for the minimization, and we got these two conditions. This is condition A and this is condition B in my hand. So with that, these conditions, if I replace it, so these are the conditions when my L will be maximized. So the maximized value of L, if I do it using A condition plus B condition into it, I get this thing, which looks a very bad, but finally it comes up a little bit simplifier, which you can further simplify because there are something to pre-compute here due to the input training example, which is our Bayesian matrix. This is a quadratic part which we need quadratic programming help. So actually we are writing it in a very simplified manner by just having two matrices of 1 cross n and a Bayesian matrix. And then after solving, what will come the values of alpha I and alpha j, because these are the only values that are floating. These are, we know as from the input examples. We will get the values of alpha I value which are greater than equal to 0. And believe me, tomorrow I will give you more insights to it. So all the points that are not contributing to the support, here your alpha I will be 0 and this only will be greater than 0 in the support. If some point is getting the support, that alpha I is only greater than 0, the rest are equal to 0. So therefore this computation is effectively computationally efficient because not all the alpha i's are non-zero here or more than 0 here. Most of them are 0. Only if somebody are the supports of this line, all of them have greater than 0. So that's what KKT theorem pushes us to. I will tomorrow explain that theorem and the converted equivalence between them. So but once we get it, we get the values of weight and B, and hence we finalize with respect to these what we call as our support line, which is also called a support vector machine model. So it's a model, it's a linear separation model that we are trying to do. So this is our support vector machine model that we are trying to find out by solving these equations. Questions? I will stop here because it's a new thing concept. So I would like to stop here. If there are questions, I can explain. Next day, I will again proceed with this. No questions? Good. That means you understood everything or you understood nothing. Anyway, yeah, Tapaddati, do you have any question? You just unmute it.
No, sir. I have understand everything. I want to tell that no question that thing.
Yeah, good. But my suggestion is that whoever whatever the last 2 lectures we are doing, do it once by your hand. The back propagation also, na, take 3-4 2D dimensional point as an example. Start with a random weight, push it forward over each example, update the weight backwards. Second example, take, push it forward, update the weight. Because unless you do this compute calculations, if I am doing in front of you, it is good, but unless you do, it will not be realized by you that what is happening. Okay, as I said, it's intuition. It is followed by mathematical concepts and conjectures to prove those intuitions you have. One of your friends started with the intuition something called a middle. I just formalize the whole thing, the middle concept, as something as a margin. We call it as a margin. So this is basically, this is the broadest margin that you can do. So we call it as a margin. This is the broadest margin that you can do with respect to the support you have, and you have to put this line in middle of the margin that you started as in your intuition. Okay, so this is the margin, or sometimes we call that twice of the margin, because we take this as a margin. So twice of the margin, this whole width. So your intuition to put the middle is perfect. Middle with respect to a margin. Margin meaning the support vectors, and support vectors are minimizing the distance, perpendicular distance from them. To minimize the distance, we need to convert it into an optimization problem from a dual to the primal problem to the dual problem. And that conversion will help us with a tool which is quadratic programming, that with respect to quadratic equation I can solve, get the W's, get the B's, get my line done. So that's it. Okay, so I would suggest neural network and this one, first try to do the equation without looking into my slides or any book. Yourself try to derive the equation, take an example, try to derive the equation with respect to that example. Okay, sit for one hour or 2 hours with this topic. This will be clear to you. Okay, thank you. That's all from my side.
Thank you, sir.
Okay, if you do not have any questions, let me stop the recording.